All right, now that we've talked about layering as a concept, we talk about the layers architectural pattern as a way of organizing software artifacts in a more systematic and orderly way. Let's talk about Android and its use of layering, because of course that's really the focus. The other stuff was just leading up to this to provide a context for discussing Android. So we'll talk about the layers in the Android software stack. You may be familiar with this diagram. If not, it's certainly worth understanding because it's pretty cool. So Android, as you probably know, is this very powerful platform for mobile app development, and now it's kind of bridging into other things beyond mobile apps. But it's basically a way of trying to systematically reuse much of the software you need in order to be able to develop mobile apps and running on mobile devices. And it's organized, as you can see here, into multiple layers of abstraction. And you can see them. They're color-coded and layered and all those good things. The lowest layer in the software portion of Android, there's actually a lower layer, which is the hardware portion, which we'll talk about later. But the software portion consists of the Android Linux kernel, which is a variant of Linux, and which we'll talk about more later too. And it's responsible largely for controlling the hardware, the mobile device hardware in particular, and managing various systems resources, things like cores, things like memory, things like the various sensors on the mobile devices, things like network communications, all that kind of good stuff. And we'll talk more about that, but that's what the kernel does. If you've taken the operating system course, this is not that different from what you're familiar with the Linux operating system. There are then several layers of middleware that provide a bunch of reusable services to the applications that run up on top. And the applications are really the apps. That's the stuff that you're more familiar with probably. But we'll talk about the middleware layers. They're quite interesting. Notice again how this conforms quite deliberately to the layering and layers architecture pattern we just talked about. So in the middleware layers, you've got this interesting thing called the hardware abstraction layer. And its purpose in life is to do two things. First of all, it adds some additional capabilities that are not supported easily in Linux, because Linux is defined, the Linux kernel is defined using C. And so you have to program at a fairly low level as a user of the Linux kernel services for various devices. You have to pass messages around using the device driver APIs, which are really low level. So the hardware abstraction layer is actually written in C++, and so it gives you an object-oriented means to access services that are not commonly found in your stock Linux kernel out of the box. So there are things, for example, for controlling the cellular radio, which you wouldn't normally find in Linux. There's things in here for dealing with other stuff, which might be in Linux, might not, but less likely GPS, camera, audio, the things that you expect on a phone but might not find on a server, for example. The second reason that there's a hardware abstraction layer is more legalistic. The Linux kernel is defined, the software written in the Linux kernel is defined using the GNU public license. And one of the consequences of that is anytime you write anything in the Linux kernel, you are obliged, because of the licensing terms, to give away the source code to what you've done. And there's some people, especially the OEMs, the Samsungs and the LGs and the HTCs and Motorola and so on, who don't want to give away all their intellectual property for all the cool hardware devices that they control. So the licensing terms of the hardware abstraction layer are more to the liking of companies that are trying to keep their intellectual property hidden from everybody to be competitive. And so as a result, the hardware abstraction layer does not require, the licensing terms of the hardware abstraction layer does not require people to give away their implementations, whereas the Linux kernel does. So that's another reason that there's a hardware abstraction layer. It appears a bit redundant, but there's reasons for it. Reason number one, object-oriented programming instead of low-level C-style programming. And number two, more generous licensing terms that companies that want to keep their intellectual property hidden may find attractive. There are then a bunch of other parts of this middleware layer stuff. We have what are basically native libraries. These are written in C and C++ typically that provide various services that are useful to people who are building higher level apps and services on an Android device. So for example, we have the libc API that gives you the C interface to the Linux kernel and the system calls. We have things like OpenGL, which is a 2D, 3D graphics engine. There is encryption and security through SSL. There's a database called SQLite that provides structured query language. CRUD services, create, read, write, update services optimized for smaller footprint devices. There's something called WebKit, which is a web toolkit that makes it easier to build browsers. It was developed by Apple. Everything in here is typically available in open source form off the web somewhere. Over here we have what's called the Android runtime, which has either the Dalvik virtual machine in older versions of Android, although there's still vestiges of this lurking in newer versions as well, and the newer version called ART, which stands for the Android runtime, which is an ahead-of-time compiled environment for taking bytecode and compiling it into native code and then executing it. So it's kind of a time-space trade-off between which virtual machine is used. Newer versions of Android use ART, by and large. There's a set of core libraries, some of which include copies of many parts of Java that we've been talking about. So Google copied large portions of the API from the Java libraries and then did some other stuff to them, but that's basically copies of Java, so a lot of this stuff will look very familiar to you. There's also other libraries that come with Android-centric classes, some of which we're going to talk about shortly, things like async task and the Hammer framework, plus lots of other stuff. And then on top of all that, there's the application framework layer. It really should be the application frameworks layer because it's not just one framework, it's lots of frameworks. And these frameworks handle all kinds of other things that Android programmers would be familiar with. How do you access the telephony capabilities provided by the hardware? How do you package your data up into structured ways using content providers so you can abstract the implementation details of your data? How do you notify things when stuff has changed? Where is your device in physical space by keeping track of its position? How do you display events to the window or windows, because Android now supports multiple windows. There's this interesting thing called the package manager, which is used when you download your Android apps from the App Store. They come down in something called the APK, which are Android packages, and there's a package manager for installing those things on the phone. There's something called the activity manager, which is basically an event bus to route events between event producers and event consumers and services and activities and so on. So there's all kinds of stuff that's provided here. And then finally, on top of all this are all the applications or the apps that we know and love and use every day. So these would include things like, obviously, browsers, calendars, email, instant messaging, SMS, MMS, et cetera, contacts. That's really what you interact with. But the apps all rest upon these frameworks, which in turn represent and rest upon the Android runtime and these native libraries in C and C++, which in turn use the hardware abstraction services, which in turn use a Linux kernel. So you can see the layering and the dependencies, and the whole idea here is to try to abstract away from things and provide a nicely structured hierarchy of capabilities. Why does Android use layering? The real question here is why would complex systems use layering in general, but we'll use Android as the example here to make the points concrete. Well, there's a couple reasons for this. Number one is it obviously enhances systematic software reuse. So one of the things that Google did when they started out with Android, which was developed now over maybe about a dozen years ago or so, going back to the latter parts of 2000 timeframe, shortly after the iPhone had come out. And they wanted to get their system to market quickly. And so rather than having to write it all from scratch, they leveraged as much as they possibly could from other sources. So obviously using things like Linux or using Java and so on, using all those native libraries like SQLite and WebKit, that made them hit the ground faster. And so systematic reuse just says don't write it from scratch, reuse it in a way that's well thought out. So that's one of the reasons why you want to do it, get you to market faster. As examples of this, libc provides a common and familiar API for accessing the operating system kernel capabilities, so why not use that, right? The virtual machine, having a virtual machine that's based on something along the lines of Java, having all those class libraries available that they copied from Java, made it possible to run applications concurrently over various types of multi-core hardware without having to reinvent all those abstractions and force the programming community to learn it from scratch. Another reason, another motivation for using layering is to enable plug-and-play replacement of certain layer implementations. So, for example, the hardware abstraction layer provides a layer of abstraction that shields the applications and the higher layer services and higher layer middleware and so on from inconsistent hardware APIs, because there really are no standard APIs in Linux, at least for talking to the radio, right? That would be weird because very few people use that on their laptops and servers. So they develop their own APIs in the hardware abstraction layer, which are more consistent, thereby allowing people to raise the level of abstraction and not get wrapped around the axle of these low-level, inconsistent APIs. The other goal of layering, of course, is to make sure that whenever something changes, that you're going to shield or confine the changes within a layer, ideally within a layer implementation, so that the interfaces don't break. So, for example, if you're going to have something where you have a new instruction, a new hardware instruction set, so you move, say, from ARM to some other programming abstraction, that doesn't break everything else in the system. You want to try to confine things to the right layer. Once again, the operating system kernel, the hardware abstraction layer are really intended to do that encapsulation. Another goal is to reduce the complexity of the APIs that the application developers have to understand. Application developers have enough on their plate trying to come up with clever, cool new features that delight users, and they don't necessarily have to want to care about all the low-level gobbledygook that goes on to access these sensors and transceivers and storage mechanisms and processing units and networking interfaces that the hardware manufacturers and device driver programmers need to worry about. Lots of low-level details. Honestly, the higher layer stuff is complicated too. It's not like people building apps have it easy, but they want to be able to work at the domain level and not wrestle with the low-level stuff. So there's a lot about trying to provide facades that simplify access to very complicated mechanisms under the hood. A good example of this, not the only example, but a good example would be the Linux system call interface. If you ever look at Linux as a programming abstraction and things like libc and so on, they have about 1,000 functions defined there. I forget exactly what the number is, but it's around 1,000. That's a lot of things to know. But compared to trying to manage device interrupts and deal with disk drives and flash memory and scheduling cores and managing virtual memory and dealing with networks, that's incredibly complicated. So that system call API is a facade that shields people from the low-level details of programming to the hardware devices. And the same idea, applies as you go up the stack. You're able to work at a higher level that's more object-oriented rather than wrestling with those, even with those function calls, quite frankly, most of the time. Another motivation for layering was to make it easier for developers on the Android platform to use well-established protocols, languages, and APIs when writing their software. So rather than forcing people to go off and learn some obscure technology like Objective-C, which is very obscure, at least for my taste, people who are programming in Android could use Java, they could use Linux, they could use TCP/IP, they could use C and C++, primarily Java, certainly for the first decade or so of Android. That was the primary way that people wrote apps. And that's very familiar. Everybody who's taken CS 101 typically knows Java or can learn Java very quickly. And it's designed to be a bit more intuitive. There's fewer sharp edges and dark corners in a language like Java than there is in a language like Objective-C, which is just goofy and bizarre, with this weird amalgam of sort of Smalltalk syntax or Smalltalk semantics with C syntax, which is very strange. Java's a lot more civilized. So it was able to allow people to hit the ground running a lot faster. And of course, all the stuff up here in these different stacks depends intimately on the lower level capabilities that are provided, particularly Java, because that's the primary way that you wrote the services and apps traditionally. And of course, these protocols and APIs are available in open source form with different licensing models, different licensing regimes, but Google has put them all together, kind of bundled them up into the Android platform. And I think you can appreciate the fact that it's heavily layered, right? That was the whole point of this stuff. So all those abstractions we talked about earlier about the layers architecture pattern and layering in middleware, layering in network protocol stacks, you see those concepts get reified or made concrete in the context of Android.